The scientific peer review system is collapsing under its own volume. In 2025, the International Conference on Learning Representations experienced a 61% increase in submissions. That explosive growth creates a severe bottleneck. A fixed pool of qualified domain experts is suddenly responsible for evaluating thousands of highly technical papers. This leads directly to reviewer fatigue, which drives a measurable drop in review quality. For an author trying to improve their work, a review that simply states, "not novel," or "needs more baselines," provides almost zero utility. It is a dead end. Compare that to a critique that explicitly names the missing methodology or points to the exact mathematical assumption that fails to hold. Specificity is the currency of academic progress. Current large language models are highly unreliable when asked to judge the actual scientific merit of a paper. They hallucinate, they miss nuanced methodology, and they diverge from expert consensus. But they excel at text analysis. Instead of using AI to evaluate the science, researchers realized they could use AI to evaluate the reviewer's text. Improving the structural clarity of the reviews is the first step to keeping the scientific dialogue functional at this scale. To test this, researchers deployed a massive randomized controlled trial during the ICLR 2025 review cycle, monitoring roughly 20,000 reviews. This design assigns subjects to a treatment or control group to isolate the exact causal effect of an intervention. The intervention was the review feedback agent. This was an automated system powered by the Claude 3.5 Sonnet model, designed to quietly assist human reviewers. The system operated under strict constraints. It remained completely blind to the paper's scientific truth. Its only function was to read the human reviewer's submitted text and flag structural communication failures. The agent scanned for exactly 3 textual targets: vague or unactionable comments, obvious misinterpretations of the source text, and unprofessional or hostile remarks. If a reviewer wrote, "This paper could use more experimental baselines," the agent flags the sentence and generates a specific prompt. It would be helpful to suggest specific baselines. Are there particular methods you feel are missing? Could you elaborate on why? By narrowly scoping the AI to well-defined linguistic tasks, the architecture bypasses limitations that prevent current AI from acting as a true scientific peer. Critiquing the writing of domain experts requires high accuracy. A single standard prompt passed to a single language model is not robust enough to guarantee the precision needed for a professional academic environment. This chart shows the 5-step multi-agent architecture the researchers engineered. It functions as a self-correcting pipeline designed to catch its own errors before a human ever sees them. The process begins with the raw paper and the initial review text feeding into 2 parallel actor models. Running 2 distinct actors forces the system to generate a diverse initial set of feedback options. An aggregator merges those distinct outputs into a single list and passes it to the critic. The critic's explicit job is to delete any feedback that is too superficial, nitpicky, or unhelpful. Finally, the surviving text hits the formatter and a mandatory reliability tests loop. If the output fails formatting constraints or tone checks, the gate closes and forces the system to regenerate the feedback from scratch. It is allowed a maximum of 2 retries. Over 96% of the generated feedback passed every reliability test and deployed to the live conference platform. This multi-agent architecture shifts a probabilistic text generator into a reliable quality assurance filter. The implementation logic was built entirely around human agency. The pipeline only triggered 1 hour after a reviewer submitted their initial draft, granting them time to correct their own typos first. This image shows the standard layout of the official review interface on the Open Review platform. It contains the traditional summary, strengths, weaknesses, and numerical scoring fields. This image shows exactly how the intervention appears. The AI feedback is quietly appended at the very bottom of the page as a private comment. It pairs the original reviewer comment with a specific, actionable suggestion. The human reviewer retains absolute control. They can manually edit their review to incorporate the suggestions, or they can entirely ignore the feedback. By framing the AI as a private, optional editor rather than a public critic, the system reduces friction and encourages voluntary self-correction. The success of the pipeline relied on a single behavioral question: did these expert reviewers actually listen to the automated feedback? This chart shows the baseline update rates. In the control group, only 9.4% of reviewers returned to update their initial text. For the group receiving the AI feedback, that rate jumps to 26.6%. Across the entire conference, reviewers actively incorporated over 12,000 specific AI-generated suggestions into their final critiques. This chart shows that the likelihood of a reviewer making an edit is inversely proportional to the volume of feedback they receive. Reviewers were receptive to a few targeted edits, but engagement dropped when presented with a long list of corrections. Updated reviews in the feedback group expanded by an average of 80 words. This growth represents substantive clarification of methodology concerns rather than minor formatting edits. When human experts are provided with targeted structural suggestions, they are willing to do the work of expanding and clarifying their arguments. The ultimate test of a peer review is how the original authors respond to it during the official rebuttal phase. This table shows rebuttal engagement metrics. Authors exerted more effort responding to AI-enhanced reviews, their rebuttals adding an average of 48 words. That engagement was mutual. Reviewers in the feedback group replied with responses 5.5% longer than the control group. Because the initial reviews were clearer, authors spent less time asking for clarification. They understood the nature of the critique and could focus their word counts on the scientific debate. Increasing the precision of the initial review correlates with more substantive engagement later. By addressing specific critiques early, authors and reviewers spent more time on direct scientific debate during the rebuttal phase. Pushing reviewers to be more thorough raises a vital safeguard question. Did this intervention inadvertently change the actual fate of the papers? The data shows no statistically significant difference in final paper acceptance rates between the control group and the feedback group. This chart shows the mean score changes during the review and rebuttal periods. The fundamental evaluations for categories like soundness and rating remained practically identical between the treated and untreated reviewers. Reviewers wrote longer critiques and engaged in deeper debates with authors, but their baseline scientific judgment of a paper's value was not manipulated by the AI assistant. The RCT successfully isolated its variable. The pipeline improved the mechanical process of peer review without skewing the outcome of the science. This deployment clarifies the immediate role of artificial intelligence in academic research. Language models do not currently possess the domain expertise or contextual reliability to act as autonomous scientific peers. The value of AI in science lies in meta-review. It operates as an untiring structural editor, strictly enforcing clarity so that human experts can communicate their work as effectively as possible.